Today we're talking about machine translation, taking a sentence in another language and turning it into an English sentence. First, we'll begin with an introduction to what machine translation is, the components of machine translation systems, and then we'll talk specifically about word-based models of machine translation, and then very briefly at the end we'll talk about how to extend these systems beyond word-based models. For many years we didn't know how to read Egyptian hieroglyphics. And the breakthrough that allowed us to finally unlock the meaning of these words was this stone here called the Rosetta Stone that had text in both Greek and Egyptian hieroglyphics. And when we found this stone, we were able to understand, finally, Egyptian hieroglyphics. This is called a parallel text because it has the same content in two different languages. And these data are what makes machine translation possible. And fortunately for us, there are a lot of organic ways that these data are created. So for example, some governments require translations in multiple languages. So for example, the European Union, Canada, Hong Kong, many newspapers have translations of the same article into multiple languages. And if you look on the web, there are many web pages that exist in multiple languages. And these parallel texts have allowed the statistical revolution in machine translation that actually makes fairly reasonable systems. So what you do is you gather up a bunch of parallel text, you do a statistical analysis of that text, and that creates a translation model. But these translation models don't always do a good job of capturing, say, selectional preferences that we talked about last week. They don't know to prefer strong T over powerful T. To capture this sort of thing, you need good language models, and these are things that we talked about before in previous weeks, and these are learned entirely on English text. And then, together, these are combined in what's called a decoding algorithm that allows you to select over all of the many different English translations of a sentence the one that best translates the foreign phrase that you wanted to translate. And so I just want to concentrate a little bit here on terminology. We're going to represent the input to the system, and we'll call that the source language or the foreign text, and we'll represent that with an F. And for the purposes of discussion today, we're going to be talking about only translation into English, but obviously the techniques here extend to other directions, but this will make it a little bit easier to talk about it. And we'll try to create English sentences E that best represent the foreign input F. And we'll call this the target language or English. And in particular, we're going to focus on word-based translation systems. What we can do is look at a big parallel corpus and figure out all the times that you saw the German word house, H-A-U-S, how many times did that get translated into various English words? And we can count that up, and then we can create a probability. So given that your foreign word was house, what is the probability of various English words being the translation? The way that we can count these things up is we need something called alignment that tells us which German words, which foreign words align with what English words. So for example, the German sentence, das Haus ist klein, you have a one-to-one alignment to the English words, the house is small. And we're going to call this an alignment function. So it's basically a mapping from every English word to some German word. And alignments don't have to be one-to-one. You can have reordering. So klein ist das Haus is a perfectly reasonable German sentence, and you have this alignment. You can also have a one-to-many translation. So the sentence, das Haus ist klein, there the final German word is translated into two distinct English words. You can also have words that drop. So das Haus ist klein may be translated as house is small, dropping the article. You can also insert words. So to accommodate this, we'll add an additional null word at the beginning of the foreign sentences. And if we have an extra word that appears in the English translation, we'll align the extra word in the English translation with the null word. So das Haus ist klein, if that gets translated as the house is just small, just aligns with the null German word. And about 20 years ago, these statistical translation techniques really began. And this happened in a fairly large research team at IBM, and they created a bunch of different statistical translation algorithms. They were uncreatively named Model 1, Model 2, Model 3, Model 4, Model 5. And despite their uncreative names, they form the foundation of all modern translation algorithms. And we're going to talk about the first translation model called Model 1 for the majority of the rest of this class before talking about the stuff that came after. What IBM Model 1 does is breaks up the translation process into smaller steps. So let's take a look at this equation. So you first have a product over all of the words in your English sentence. And each of these English words is assumed to come from some foreign word. So which foreign word did it come from? It came from the foreign word that the jth English word was aligned with. And so you look up that word in your foreign sentence based on the position of the alignment, and then you can look up the score. What is the probability of getting English word J from that foreign word based on the alignment? And this is just a probability. We represent that probability with a t. This is parameterized by an English word and a foreign word. You can just look up that probability. And then you have a normalization constant that makes this all sum to 1. And then you have the probability of all of the alignments, and the total number of the alignments possible is the length of the foreign string plus 1. So the plus 1 is there because of that null word that we added. And that's to the power of the length of the English sentence, because each foreign word can be aligned to one of the English words. And the number of words is just the length of the English sentence. So let's take a look at an example of this. So let's say that you have Das Haus ist klein, and the alignment is the one-to-one translation, the easiest one that we saw. And so here we have, there are 4 to the 3 possible alignments. So the first probability is epsilon over 4 to the 3, and then you multiply that by each of the word translation terms for the probability of the given das, the probability of Haus given Haus, the probability of is given East, and the probability of small given Klein. And so that gives you some value as 0.0028 times epsilon. Okay, so that's how we score a translation if we know the parameters t for this translation model. But how do we learn those parameters? And so it would be easy to learn those parameters if we had the alignments, but we don't have the alignments. So this is a chicken and egg problem. If we had the alignments, we could get the translation probabilities. If we had the parameters, we could get the alignments. So a common solution when you have this kind of problem in statistical machine learning is to apply the expectation maximization algorithm. And so what you do is you initialize your model parameters somehow, and then given those parameters, you compute expectations over what you think the missing data should be. In this case, it's the alignments. And given those alignments, given those missing data, you compute your model parameters given those complete data. And then you repeat those steps until you get a final answer. So in this case, what we're doing is we're trying to figure out alignments. And so we start thinking that all alignments are equally likely, and then we learn translation parameters given those alignments. After one iteration, we learn that the probability of getting the word the given the foreign word la is higher, and so that changes our idea of what the alignments should be. So we'll think that the expected number of alignments where the aligns with la is going to be higher. And given that we know that the should align with la, that will make other alignment positions more compatible. So for example, we'll prefer that fleur and flower get aligned. And then finally, we'll get a converged answer where we prefer, very specifically, some words to align with other words. And this is what can happen with EM. And from those good alignments, we also get good parameter estimations, in this case, the word translation probabilities. Okay, so more concretely, the EM algorithm consists of 2 steps. First, the expectation step, where we apply the model to the data and we get out of that the revealed hidden structure, in this case, the alignments. And given those alignments, we compute the model parameter, in this case the word translation probabilities. And so we just take the alignments that we get out of the expectation step as truth, and given those alignments, we compute the translation probabilities. And we just repeat these steps until we get a final answer. And so there are two steps that we need to do. We need to do the expectation step. What are the probability of alignments? And then we need to do the maximization step, which is basically just counting up the number of times that words get aligned to each other. This is a very brief example. So given some initial word translation probabilities, we can compute the probability of alignment.